Okay, good afternoon, everyone. Time to get started again. So this unit is about model order selection, and we went through an important derivation last time where, well, I guess last time we did a lot. We talked about random variables, talked about expectation, which we're using a lot in our derivations, conditional expectation as well. And then we built a statistical model that is going to be sort of a way to think about a lot of concepts in this course, so maybe we'll just talk about this again. So we have a true model, and we have a prediction model. In the true model, there's some true function f plus noise, which relates our features to our labels. So this true model is deterministic, but we don't know it. We have a prediction model f hat, which may be very different from the true one. Our prediction model depends on some coefficients beta, which we have learned from the training data. So we assume that that process is already done. And the prediction model puts out y hat. We hope y hat is close to y. Now, a few important points. We're going to assume that our noise is zero mean. The variance is just some number sigma squared. We're going to assume that several things here are random variables. So the noise will be a random variable. The features will all be random. The labels will therefore be random. And this model applies to both the training data and the test data. And when we talk about training data, we have subscript I on everything. We talk about test quantities, we don't. But we think of the training data as random and the test data as random. And maybe one way to think about this is when we do some of the demos in the course, like especially this polynomial demo, in that case, the data is generated randomly every time you run the Jupyter Notebook. So there is some distributions that never change, like the features are always uniformly distributed. The epsilon is Gaussian distributed. That's fixed every time you run the demo, but every time you run it, you get a different realization, a different set of numbers for x and epsilon and y. So you get slightly different results every time you run the demo. We want to know things like, how good are things working on average, imagining that I would run this demo, many, many times, and I want to know what's happening on average. That's when it helps to think of these as random variables. Every time you run the demo, it's just one set of fixed numbers, but across many runs of that demo, you can think of them as random variables. So that's our goal. And then finally, the performance metric that we care about is the mean squared error when we talk about regression. This is the typical one. We want to know what is the expected value of the squared error between the true and predicted targets. And for our derivations, it helps us to first think of x as fixed, even though it is random. For our derivation, we temporarily think of it as fixed by conditioning on x. We can derive an expression for the MSE that depends on x. Once that's all done, then we can come back and say, okay, now let's take an average over those x's. And then you can get an MSE that is the average MSE that doesn't depend on x. So that would be like, because you never know really what your x will be at test time. So you might not care about what happens at a particular x. You care about what happens on average over the x that you get in your test data. So that's sort of high level. Any questions about the model? Everybody good with this? Okay, then we went through this long derivation. And in doing it, the main things we used was linearity of expectation and the independence property that allows you to decouple expectation when it's the product of two independent statistical quantities. And the outcome of all this was an important way to break down mean squared error into three terms. First term is the irreducible error. Second term is the bias squared. And the third term is the variance. So let's talk about the irreducible error. So when we come back to this model, we see that in the very best case, if somehow I can construct my function f hat here so that it's perfect, so that this is exactly the same as this. In that case, my predictions will get this part perfectly right, but I will never be able to predict this noise because the noise is independent of x, and so I can't ever predict the noise. That will always be there. So the difference between y and y hat, in the very best case, will include epsilon. And when we square that epsilon, we know that we get a variance on average, sigma squared, and so that is where this comes from. This is an irreducible error where if everything is perfect, that's the minimum we can get. Okay, now, in general, things are not perfect. We have bias and variance. So the bias tells us whether the prediction error is 0 on average or not. So if the prediction error is 0 on average, which is actually something that happens pretty often, if we have a powerful enough model, we can set the bias to 0, and that means that this part of our mean squared error is gone. In that case, the only thing we have left is the irreducible error and the variance. Okay, so to get the bias to go to 0, that's what we call when the estimator is unbiased, or the predictor is unbiased. For that to happen, essentially the true model needs to be within the realm of possibilities of our predicted model. So our predicted model can take many forms depending on how we choose our betas, but the way it usually works is if there's one of those possibilities that includes f, then when you take this expectation here, you'll eventually find that the error goes to 0. At least that's what happens with linear regression, as we'll see. So it is possible to get your bias to 0 with a more complex enough model. That leaves the variance term. So the variance term is just to recognize that it's not enough for your error to be 0 on average. You really want to know what your error is on any given experiment. So, because you don't care what happens if you average over experiments. It's just like, at the end of the day, you're going to have one thing you're trying to predict. Someone's going to give you one set of numbers. You want it to be 0 for that. So there's what happens on average, but then there's the deviation from the average. And that's just what the variance is measuring. It's the expected squared value of the difference between the the prediction and the average prediction. So the larger the gap between prediction and the average prediction, the larger your variance grows and the larger your mean squared error grows. So we saw some examples of this here with our demo. So there is one more mistake that I realized today. So this should actually say expected value of y given x. So that's the red curve. For our polynomial model, this is, or for this statistical model here, this is just going to be our true function f, which for our polynomial demo is that cubic function. So that's the true thing. Remember, though, that the data is not expected value of y given x, it's y given x. And when you look at the data, it's a whole bunch of points that are around the cubic, but not exactly at the cubic. So this is what we're shooting for. If our predictor was designed perfectly, it would be that cubic function, right? And it would be that always, without any exception, at which point our mean squared error would simply be the reducible error. Okay. But that's not what's happening here in any of these cases. So in the first case, this is when we choose a model order of 1, which, as we know, means a linear model or a line, regression line. We see that on average, we're not getting the correct curve. On average, there's a gap. So what do we mean by this? So the solid green curve here, that is this expected y hat given y. From a practical perspective, it's like this. To create these curves, I ran this experiment 100 different times. Every time I ran the experiment, I generated a whole new set of data, a whole new set of x's, y's, calculated a new beta hat, did a new set of predictions, measured mean squared error, all that stuff 100 different times. Every time I did that, I got a slightly different regression line. Kept moving around. So what I'm showing you here is the green curve, or the green line. That's the average of all those regression lines. This is the average regression line. It was never the regression line on any given experiment. It was just the average over all my 100 experiments. So that's what we're plotting there. But then these little error bars show you how much deviation from that average we saw across all those 100 experiments. So you can see that there was a bit of tilting in the line and a bit of shifting of the line. So it's always a little bit different. That's what those little error bars are showing. In any case, we have bias because there's a gap between the red and the green, at least for most of the x. If we think about bias as a function of x, then we could say that at this x, when x is 0, there was no bias. And at this x, there was no bias. Those are very special cases. Probably not going to get one of those x's in practice. So in general, yes, we have bias because we have gaps between the average y and the average y hat. Okay, so now, next we do this experiment over, but we use a polynomial prediction model. So every time I fit the data, I got a slightly different polynomial curve, and then I average that over 100 experiments, and we get this green curve here, the solid green curve. That's the average. But as you can see from the little error bars, there was a deviation from that average. So, we never got this green curve on any one experiment. We always got variations of it. But at least if I look at the average over my experiments, it seems to be matching the red curve perfectly. So when we had enough coefficients in our model to express the true model, on average, we're doing the right thing, which is great. But on any given experiment, we wouldn't be doing the right thing. There would always be a little difference from the average, and that is what the variance is capturing, or the square root variance here, and that is what we're plotting with those little error bars. So they're showing how much variance you get. And remember, again, if you care about mean squared error, we're saying that in that case of d equals 3, this one goes to 0. But we do have something from this, and we have something from this. And the amount from this we can see here just visually in terms of these little error bars. Okay, so which one of these will have lower mean squared error? Left or center? Center, right? Because the mean squared error is the bias squared plus the variance plus irreducible. And so this one, the error bars are around the same size. So here, this guy is going to suffer mainly from this bias squared. This one doesn't have any bias. So yes, this has lower mean squared error than this. Okay, now we did another experiment where we used a 14-order polynomial model. It's a very complicated model. In this case, we see again, no bias. So the average prediction curve is matching the red. That's great. Bias is going to 0. But what about the variance? We can look at the little error bars and we see the variance is actually much larger here than it was here. So which of these two is going to have higher mean squared error? The right one has higher mean squared error, exactly, because they both have the same of this, but the right one has a higher variance. Okay, so among these three, this will have the lowest mean squared error. That's the one that we would prefer. That's the one that, as we see, happens to have the correct model order. So when we do model order selection, this is what we're trying to do. We're essentially trying to navigate some balance between bias and variance. It's not always the case that you can set your bias to 0. In a lot of complicated models, you can't really do that. So as you get a more complex model, your bias goes down, your variance goes up. You want to find the place in the middle where the sum is the smallest. Okay, so and then these are just some visual descriptions that show us examples of throwing darts at a target where you have small variance, so points are in a tight cluster, but here a large bias. And then this one is low bias, low variance. And then this one has no bias. On average, you're hitting the middle, but you can see the variance is much larger. So those are sort of another way of thinking about what's going on here. Okay, so I think this is a super useful experiment to understand all these concepts. questions from you guys? Is this making sense, mostly? Okay, good, yes?
Are we able to see the irreducible error graphically? Or?
It's, yeah, I don't think we're seeing it here. Yeah, we're not seeing it here. As far as I remember, it's, yeah. I don't think it's going to be, it's not going to be part of these little error bars. Those are just on the model itself. So yeah, good question. We're not seeing it, but it's there. Okay, any other questions? Yes?
Could you tell a bit more about bias, like factor bias?
Well, yeah, so the bias is, there's kind of, you can think about it in terms of the y's or in terms of the model's f. But so the bias, you know, y minus y hat, that's the error, right? But we're looking at the average value of that error. So if, like, when I do my experiments, like this time it's maybe the error is positive, next time it's negative. And if I keep averaging over all my experiments, maybe it's on average it's 0. It's like, you know, half the time it's too big, half the time it's too small, but on average it's right.
So how is it different than the standard deviation?
Well, the standard deviation is measuring how far away from the average you are. So this is measuring the average. And like we can think about it in the y's, or we can think about it as fx, which is the noiseless model, and f hat. F hat is our prediction. So this is like our average prediction, which is that green solid curve. And then this is the noiseless model, which is the red solid curve. So yeah, this is basically telling us some quantity that is describing the average behavior. And the standard deviation or variance is all about how far things are from the average. So over here on the right, we have the difference between f hat and its average. So pictorially, it's like in this case here, the average f hat is that green line. But if I think about the different experiments I ran, sometimes I would always get lines, but sometimes they were tilted and shifted in different ways. So if I want to know, like, how much do those red lines vary from the green line that's their average, that is exactly what we're measuring here. Okay. All right. Good. Any other questions on this stuff? Yeah.
Can bias and variance be thought of as accuracy and precision?
I don't know. I mean, I think they're a little different, I guess. Yeah. So I probably wouldn't recommend that exactly. I do think, well, to me, accuracy. So mean squared error itself is like average accuracy. Precision is kind of like just how much information you're reporting. You know, it's like if you round off your estimate to make a nice simple number, right? That's like low precision. You're kind of throwing away all those extra decimal points that really are there. Yeah. Okay, great. Any other questions? Okay, so so here's another question as you look at this and look at the equation. Which one of these things would change as you get more or less training data? So let's say I said you have like tons of training data. Do you expect to see some advantage in terms of bias or variance or irreducible error? Which would benefit from having tons of training data? Someone thinks bias. How many people think bias? Okay. How many people think variance? How many people think irreducible error? Okay. So it turns out that the right answer is the variance component. The bias is really just, bias is not typically affected by the number of training samples. It's really about whether your model itself is going to be complex enough so that it can describe the true model. You know. But the variance is, as we'll see, it's definitely related to the amount of samples, training samples you have. Okay, So, so we can see this concretely if we look at the special case of least squares linear regression. So in our previous case, it was just a very general model. We made no assumptions on what f and f hat were. Now we're going to be a bit more specific. We're going to say that f is this very familiar model from multiple linear regression. So there's the betas, there's the feature data xij, and notice that there's this true model order, d true. And we're going to assume for this derivation that we have Gaussian noise, which we didn't need to assume the distribution before, but we're going to assume it's Gaussian. I actually don't think that I don't remember if that's actually needed for the derivation, but as before, zero mean sigma squared variance. But then for our model, we are also going to assume a linear model, but now the difference is we may not have the true model order. So we're going to have just some generic model D. And as always, we have n samples in our training data set. So let's break this down into 3 different cases of what can happen. The first case is when we have n number of samples in our training set less than the number of features plus 1. So do you remember what happens in this case? Like, what's the shape of the A matrix? What are the dimensions? Is it square? Is it tall? Is it wide?
N by D.
Yeah, it's right. It's n by d plus 1, so it's a wide matrix. So basically, you have many more things, predictors, betas you're trying to learn, and not enough data to learn them, right? So it turns out there's actually many different betas that will give you the same targets y hat. So there is no unique beta hat. So there is no unique least square solution. There's many least square solutions. They're all going to give you the lowest RSS, but you don't even know which one to choose. So for this, we're just going to say we can't really analyze this model because we don't even know what the least squares training coefficients are. Okay, so that's what happens when you don't have enough data. We'll talk in the next unit about some strategies that you can use in practice when this arises. It's not the typical thing in machine learning, but it definitely is there for some problems. Okay, so for the other 2 results, we're going to assume we do have enough training data. And although I didn't write it here, we're going to assume that the matrix we need to invert for the least square solution is invertible, in part because we have enough training data, but we don't have any, it's not like all our training features are identical, because that would also give us problems. Okay, so let's assume enough training data, but then let's look at what happens if what we assume for the model order D is strictly less than the true one. So in that case, it's not difficult to show that your model, your y hat, will be biased, and you will get underfitting. Underfitting is just kind of another word for bias because your model is too simple. On the other hand, if D is greater or equal to D true, then your y hats are unbiased. And by unbiased, we just mean that the bias is 0. This is the same bias that we had on the previous slide. It's just now it equals 0. Okay, so that happens when D equals D true, but it also happens when D is greater than D true. And we saw already an example of this. In fact, you can think of this as a special case of linear regression, right? Where you created these x's using powers j of xi. Right? That we saw that polynomial regression is, you can think about it as linear regression just by creating features that have the different polynomial powers. So that's sort of an explanation for why in these 2 cases we had a perfect match on average, why there was no bias. Okay, but now we're looking for that last explanation. Why did the error bars grow as we went from 3 to 14? Okay, and that's this last result. So this one takes a little bit more work to derive. It goes kind of like this. If you have a lot of targets, and this is just to do the derivation, and you have equal or greater model order than the truth, and a few other technicalities like your test vectors come from the same distribution as your training ones, then you can show this super interesting result that the average variance is d plus 1 over n times sigma squared. So this gives a huge amount of intuition for several things in machine learning. So from this right away, we can answer the question that I posed to you before, which is, what benefits when you have more training samples? So here, if we assume that our model order D is fixed, our noise variance is fixed, all we're going to do is increase n. You can see that that's going to make this smaller, right? If I double n, I'm going to halve my variance. So it's crystal clear what happens in this case, like why you benefit from more training samples. Another way to look at it is, what if I fix my training data set and I change my model order? I go from 3 to 14, as we saw in the previous slide, right? In that case, you can see the penalty that this is going to grow, and so your variance is going to grow, and your mean squared error will grow. Right? So you can think about it that way. Another way you can think about it is, what role does that variance on my noise epsilon play? Well, if my variance on epsilon doubles, then my overall variance of my prediction will also double. So you can see how this plays a role as well. Okay, so this is like super useful, I think, super important equation to give us intuition about why in machine learning we want large training data sets, why we want to do model order selection, why we don't just always choose the most complicated model that we can. It's because it will hurt you, it will increase your variance. So the simplest explanation is the best when that simple one is good enough to explain the phenomenon, which is the true model. Okay. All right. So all the details of this are in a, let's see. It's a few pages long. I think this is the one. Yeah, it's a few pages long. It's nothing really complicated. It's a lot of the same stuff with linearity of expectation and stuff. There's a little bit of linear algebra in it, but all of you guys are completely able to understand this. It is optional, though. You don't have to look at it if you don't want. Okay. But that's there. The derivation is there in that document if you want to take a look. All right. Any questions on this before we move on? Yeah.
Is this for linear regression or for polynomial also?
Well, you can see the assumption is, this is the assumption. So in the sense that polynomial, you can just think of forming these from polynomial data, then yes, this works for that too. Yeah. So anything that you can write like this works. Okay. And so this is kind of just a slide that puts in a picture what I've been telling you the last few minutes. So, we've been looking at polynomial and then linear and so on, but these kinds of things apply in many, many different machine learning problems that might be more complex than polynomial or linear. And the general type of trend you see, so this is sort of the guiding equation. This is what we've seen before. Mean squared error on the target's y is going to be the irreducible error plus the squared bias plus the variance. And here I'm using expectations because first we're thinking of deriving these based on a fixed x, but then we're saying I actually care about what happens on average for that x. Okay, and the picture that you tend to see looks like this. So we have model complexity growing from simple model to complex. You have mean squared error here. And so this is an illustration, just a rough drawing of what the squared bias might look like. So generally speaking, as you make your model more complex, your bias decreases. Eventually, it may plateau. In the special case that we saw of linear regression, it might do something like this, go to 0 and then stay at 0. But it really depends on the details of the model and the data and all that. Then the variance term is something that tends to increase as your model increases. And in some cases, like we derived a very specific equation, but that doesn't hold always. So in general, variance is something that tends to grow. But we actually care about the sum of those, and that's what's illustrated pretty roughly by this black curve. So generally speaking, there's going to be some sweet spot in your model complexity trade-off where your model is, if your model is too simple, variance is great, but bias will be killing you. If your model is too complex, bias is great, but variance will kill you. You want to be in the middle where you have some good trade-off between those two parameters, or sorry, those two components of your mean squared error, and that will give you the lowest mean squared error. Okay, so this is just sort of a general trend that we're going to see a lot of as we go through the course. All right, any questions on this? Okay, so here's a very important slide. I think conceptually we'll tie several things together. We can apply these notions of bias and variance to our sample estimators. The sample estimators were the things we talked about way back in Unit 1 for the scalar case. And so let's revisit that, but now let's bring in the concept of randomness that we just introduced more recently. So imagine that I have a random variable z, and this random variable it can come from any distribution. It can be Gaussian, it can be uniform, it can be whatever. And let's just say that we'll call the mean mu, and we'll call the variance v. Those are just some numbers. And let's suppose that in practice, maybe this random variable is describing some physical process, and I want to learn about that physical process, so I take a lot of measurements. And in terms of statistics and so on, we think about those measurements as realizations of the underlying random variable. So the underlying random variable is what's really there in nature, which we would like to know about, but we don't know what it is. So we take a bunch of data, and the simplest thing we might want to learn is the average value. So z is, z is describing some real number, and you want to know what is that z on average? Well, you take n different measurements of it and estimate the mean from that. So the favorite way of estimating the mean, as we know, is the sample mean. You just simply add up those numbers and divide by n, the number of them, right? And you might ask then the question, well, how good is that? Is that a good estimate of the true mean mu, or is that a bad estimate of the true mean mu, right? So one of the things, to answer this question, we first have to say, well, wait a minute. Okay, if I treat these z's as deterministic numbers, I can't really say much about them. It's just some list of numbers. Like maybe when I took that measurement, it happened to be good, a good estimate of the true mu, right? But the question is, well, what if I got to do this again tomorrow or the next day? Would it always be good? So in order to answer that question, we actually want to think of these z's themselves as random. So even though here I said that they're realizations of z, and I'm using a capital Z here meaning random and small z here suggesting deterministic, for this analysis, I actually want to think of my realizations themselves as random variables. Okay, and I want to think of them as having exactly the same distribution as z itself. So if z was Gaussian with mean mu and variance v, then I want to think of these zi's as Gaussian with mean mu and variance v, and I want to think of them all as statistically independent of each other. And at that point, is z hat deterministic or itself random? Random, right? If all of these zi's are random, then when I average them, this is random. And now that this is random, I can actually think about what is its average value. Again, saying like if I did this experiment today and tomorrow and many, many times, would I get a good estimate of the true underlying mu or not? And so when we say good, we can again think of this in terms of is it good on average and how far does my estimate stray from that average any given time. So good on average is asking is z hat biased or not? It's asking does the mean, the expectation of z hat match the true mean? Okay, and that analysis is actually relatively easy. Let's just imagine how you would do it. So I just want to compute expectation of z hat or z bar. So as we know, that means I would be looking at this expectation. And what's the first thing I could do to simplify this? Yeah, I move the expectation inward, linearity, right? I can then do expectation of this. And I know this, right? What is that? Mu. That's mu. I said that those zi's are all random variables with mean mu. So this ends up being mu, and now I'm taking the average of mu, which is just mu, right? So finally, at the end of the day, this measurement that I'm taking, which is always a little different, on average, it's correct. It's unbiased. That is one of the main reasons people use this as the estimator of the mean. Whenever you want to learn something and you collect a bunch of data and you want to learn what this thing is on average, you just average your data samples. Simple as that. Okay? So it has a nice foundation as being an unbiased estimator of the true mean. But we said that that's not enough. We actually care about whether my z-bar is correct for a given measurement. So for that, I want to know how far does it stray from this perfect average mu. So what I can do is I can look at the variance. So here the variance, as we know, the variance of this z-bar. I take z-bar, I subtract its expectation, which we just derived as mu. I square it, and I look at the expectation of that. And this derivation is a little bit longer, but I can show you in another handout how to do this. And what you find is that this variance is v, which is tied to how much variation the random variable z itself has, divided by n, which is the number of samples. So what does this tell us about how we want to choose the number of samples when we do this average? Do we want a few samples or a lot, or does it matter?
More samples.
More samples.
More samples, right? If I could take an infinite number of samples, I could reduce my variance all the way to 0, at which point my mean is matching, my variance is 0. I have a perfect estimate, right? Perfect estimate. So the problem, though, in practice is we can't take an infinite number of measurements. We're bound by complexity or cost or whatever to take only n. But at least this tells us how good of a result we get. How much can I trust the z-bar that I computed from n measurements? And this is exactly the concept of standard error, which we saw before. In fact, if you just think about this not as a variance but a standard deviation, take the square root, that's the square root of v over n, right? That's the equation we saw for standard error. The way we wrote it there is it was standard deviation on the top, and on the bottom is square root n. I think we used k when we did it last time, but k or n is just the number of terms in the average. It's the same thing. Okay, so now we actually understand what does that standard error tell us? It tells us whenever we compute a mean from a finite number of observations of some random thing, n in this case, it's not going to be perfect, but we can actually measure its imperfectness and we can quantify it as this quantity, standard error. And that is why pretty much in any paper you look at that has error bars on a curve, they're almost always standard error bars because they did some experiments where they acknowledge that the results are finite, so they don't know the truth, but they can at least tell you based on the number of things we collected, we have this much confidence. Okay, so that's really what standard error is telling us. And that's why we use it sometimes in our pictures and sometimes in our our one standard error rule and so on. Okay, so that's super important concepts. Any questions on that? Okay, so here we set out to estimate the mean, estimate mu. That was the goal we set out to solve. Sometimes you actually want to estimate v. There's some true variation, and you want to figure out what it is. In fact, we had to do this even when we computed standard error, right? Because no one told us what the statistical variance of v was. That's something we actually had to learn from the data ourselves. No one told us. So that's actually a nice problem. Given a bunch of data that has variation, estimate how much variation there is, estimate that variance. And again, we're given the same data set. So back in Unit 1, we learned one way to do it, which was what we called the sample variance. And that was this equation. And at the time, I mentioned to you that sometimes people use n there, and sometimes they use n minus 1, and I said I would tell you about it later. Well, now is the time. So this is just one way to do it, right? Now, this is, again, going to be for one set of data, you're going to get this one number, which is an estimate of the variance. You may or may not know the true one. In reality, you don't. But let's say a genie told you what the true one was. You know, sometimes this would be above, sometimes it would be below. It's never going to be perfect. So you might say, well, how good is it on average? On average, is this going to match this or not? So that's the question of bias. Is this a biased estimate of the variance or not? So to figure that out, what you do is you just take the statistical expectation of this quantity. Again, we're thinking about all the zi's as random. Z bar is therefore random. And so it's a little bit longer of a derivation. I can show you in a moment. But it turns out when you do this, you find that it's not exactly V. It's a little bit less than V. And how much less actually depends on the number of samples you take. So this is a biased estimate. You would say it's asymptotically unbiased, and that as n goes to infinity, eventually that bias goes away. But for any finite n, this is strictly less than 1, and so it's not quite right. It's not quite right on average even. It's systematically a little bit below. So you might say, well, I don't like that systematic error. I want to correct this so that on average it's at least correct. And then sometimes it's going to be above and sometimes going to be below. That's fine, but at least I feel good knowing on average it's correct. So to do that, you instead come up with a slightly different estimator, where all you do is you change the n to n minus 1. And when you look at the average value of this, you see that it's exactly V. It's exactly true on average. And so this is what we call the unbiased estimate of the variance. Okay, so that's kind of bringing back this notion of these two different standard deviation or variance estimates and why one is biased, why one is unbiased, what that all means. Okay, so good point to pause. Are there questions on these concepts? Okay, so we're kind of taking a closer look at these sample estimators. Now, one final question you might ask, very good question, is which of these two things is better to use? Is it true that the unbiased one is always better than the biased one? What do you think? How many people think we should always use the unbiased one? Okay, how many people think we should always use the biased one? Okay, no one's willing to venture a guess here. So it really depends on what you care about at the end of the day. One of the things we've been focusing on at the end of the day is mean squared error. So if you care about mean squared error, you don't care about bias necessarily. You care about the difference between the estimate and the truth squared on average, right? And as we know, there's another way of thinking about that, which it decomposes that into the bias of our estimate squared plus the variance plus any irreducible error there is. So it turns out that you can do this computation. You can compute the expected, the mean squared error on the first guy, and you get this number. You compute it on the second unbiased estimate, you get another number. And it turns out that this unbiased one is actually, it's worse in terms of mean squared error than the biased one. Why do you think that is?
The squared term and the biased estimate, as you get more samples, go lower, I'm assuming?
Something goes lower. I'm listening for a magic word. So what is the advantage of this biased one? Clearly, its bias is higher than the unbiased one, but what is its advantage? It has an advantage. We have a word for it. Mean squared error, you can decouple it into what?
Bias.
Bias and?
Variance.
Right. So what do we conclude about the variance of the biased one versus the variance of the unbiased one? Which has a lower variance?
Biased.
The biased one, right? Exactly. So that's the trade-off. This guy has a great bias, or has a bias, which is bad, a high bias, which is bad, but a low variance. This other guy has a low bias, but a higher variance. And when you put them together in mean squared error, you actually find that the first one wins, the biased one wins. So again, which one you use kind of depends what you care about. If you really care about mean squared error, use the biased one. If you really care about bias itself, use the unbiased one. And there's no like, I think it really depends on the problem. It really depends maybe what you care about. There's no automatic solution, and that's why you see a lot of disparity in the literature about which one you use, this versus this. It just kind of depends. Okay, and yes, the details are in this handout. This handout, yes, this one I think is more important in the sense that it's a lot simpler than the other derivation. It's pretty straightforward, and it uses a lot of tricks that show up on homeworks and exams. So if you find yourself kind of like stuck on some of the homework problems, you may find a lot of the solutions to those issues are in here. This is, again, nothing that you guys can't do on your own. Let me just kind of maybe go through this just a little bit, and I'll show you what I mean. So this is the part, we actually already did this derivation on the slide, but this is where we're looking to see what is the mean of our sample estimator, and we saw that's just the expectation of the sample average. And finally, we were able to show this is unbiased. By the way, this is actually a good point to reflect on the differences between the two kinds of averaging that we have, right? We have a deterministic averaging, sample averaging, and we have a statistical averaging. We can see that they're similar in spirit, but they're actually mathematically very different. One of them works on random variables. One of them works on actually anything, random or non-random, right? But this is something I've seen a lot. Maybe it comes up later on an exam, but a student doesn't understand the difference between a sample average and a statistical average. So this is important. Please try to think about this, reflect on the difference between the two.
Could you really point to which one is which again?
So this is what we call the sample average.
Okay.
Just, it's done with samples. Or sample mean, right? It's written here. Sample mean, sample average, same thing. And then the statistical mean is this one. Two different kinds of ways of thinking about an average. Okay. Okay. So this part, I think this was pretty easy. Again, in terms of like the raw skills, this is just linearity of expectation. Pretty simple. What about this next derivation? This is a little bit more complicated, but worth going through. So when we wanted to compute the let's see. So this is, we were looking at the variance. Okay, if I put a 1 over n here, this guy is just going to be my sample variance of the sequence xi, right? And so, and for the derivation, I'm leaving out the n to make things a little simpler. So let's see how we do this computation. Okay, so the first step, linearity of expectation, right? Bring this through. We have now a sum of expectation. Second step, as we've done many times, expand this quadratic. So you have the first term squared, the cross terms, the last term squared. Okay, now, again, linearity of expectation. You can take the expectation of this minus 2 times the expectation of this plus the expectation of this. So that leaves us here. Okay, now it becomes a little more interesting. So what about this term? We've seen this before. Does anybody remember off the top of their head how we do this? When you have expected value of something squared, it's, how do we do it in terms of the mean and variance of xi squared? Yeah, it's the variance of this thing plus the square of the mean. So, right? So this is something that comes up very often, so you want to be able to just go to this immediately. This is a good thing to memorize. Okay, what about the second term? Can we split this into a product of two expectations? Why or why not? What are we looking for when we trying to figure out, is this the product of the two expectations? We want to know whether they're what? Independent or not, right? So what do you think? Is xi going to be independent of the sample mean?
No.
No, and why not?
The sample mean kind of, I mean, it's representing all of the individual.
Well, in particular, the sample mean is,
Like,
it includes xi. It includes a bunch of other xj's that are j's not equal to I, but it includes xi. That's what's important. So those are coupled. They're statistically dependent. So you can't, unfortunately, just decouple this. We have to do a little more work. So this is how we can do that work. This is what we do here. So the first thing is we can expand x bar into an actual sum. And so we have to be a little careful here. Since I already means something, I cannot use I for the sum. That would get me in big trouble because now this xi is actually different than this xi, even though I wrote them to be the same thing. So make sure you choose the variables for your temporary variables for your sums carefully so they don't clash with other existing variables. So we use j here. Hey, now you can see this is another easy expectation thing in that we can move all this stuff through, right? And now we get expected value of this. So here again, we ask the question, is this independent of this? Yes. Is any no's?
For different time.
Yeah, so I think it depends on j, right? So this, I didn't write it explicitly, but there's like j equals 1 through n. So one of these j's is I. So one way to handle this is to break the sum into the j not equal to I and then handle the I term separately. That's a good approach. For this, beforehand, I kind of thought through this earlier because it's used several times. And I said, okay, there's basically two cases. When j equals I, this is expected value of xi squared, and we know the equation for that. That's mu squared plus v. So this little thing, this is called a Kronecker delta or different names for it, but this is a little thing that comes alive when I equals j, an indicator function. So when I equals j, this comes alive and you get mu squared plus v. Now, if mu is different from, if j is different from I, then they're independent. Then I can just look at the product, and they have the same mean, which is mu. So you just get mu squared, and this term goes away. That's because this went to 0. So this is a concise way of writing this for general I and j that may or may not be the same. So that's what I used down here. I plugged in that expression, I plugged in that expression. And then I did this separately on either one. So this guy comes alive only once over this range of j. Whereas this guy, you can see, is the same for all the numbers in j. So in the first one, the n went away, but in the second one, the n did not go away. Okay. So now, is everybody okay with this? And again, this is the kind of stuff that shows up a lot in homework and tests. So come back to this if I'm going too fast right now. Yeah.
What's the upside down capital A?
Oh, great. So that's for all I. So yeah, sorry about this. So like this equation here, I'm saying for all I this holds, not just for one special I. Okay, so the last thing, let's go through this because this is also important. We need to take the expectation of this x bar squared. So this is a little bit more tricky. So x bar itself, we have to unpack that. So that's this average thing here. So this goes from 1 to n. And so here we want to square the whole sum. So we have to be careful. Perhaps one thing we could do just immediately is I can just pull the 1 over n out of the squaring. Then it turns into 1 over n squared. And then I can pull that out of the expectation, and it lives out here. And then we can just look at the sum itself squared. So here's a common mistake that students make, is they just write the sum over j twice in a row. The problem there is you're using j to mean two different things. But there's one j, two different things. So you can't do that. You have to, when you write this the second time, you have to write it with a different index. Because I is not being used anywhere, I'm writing that over I. So this is sort of shorthand for xi, sum over xi, xj. So that's what I did. So super important, when you do squared sum, you write that sum twice, but with different variables. Then the rest of it is easy. Once we have this, we can pull this out by linearity, and then we have the expected value of this product, which we saw before is this. And after that, it's not difficult to carry out the sum and so on. And finally, you get this expression. And this is, on our way to deriving the bias of the variance estimator and so on. But it's really, I think the reason I want you guys to look through here is because there's a lot of tricks that you will, in some sense, need to learn, to handle the kind of things we want to do in this course. So once you see these tricks, if you can do the tricks in this handout, you can handle all the homeworks and exams fine. So I think that's enough for today. Any last questions? Yeah?
Quick, what prevents the assumption of just saying I equals j, where you kind of wrote blue there below? I don't understand why we have to use two different sums.
Oh, I see. Because, so, sorry, I meant to erase it. Okay, so when you do something like this, if you really think of those sums as isolated and you really don't merge them at all and work with them together, that's okay. The parentheses are kind of like saying, just think of the sum on its own. Don't get distracted by anything else. But if you take off those, if you take off the parentheses and you start moving sums around, which you can usually do, right? Then all of a sudden you get stuff like this. And then maybe you do, okay, that's xij squared. And then you have this, what does that mean now? 2 sums over j, xj squared. Like it just starts to get into mathematical nonsense land. And you can come up with like a lot of incorrect things when you go down that path. So that's the kind of danger you get into when you start mixing the things with the same variable that mean different things. Yeah. Okay, thank you. Great question.